So in the previous lecture, we saw Quicksort, which works as follows. You first rearrange the elements with respect to a pivot element, which could be, say, the first value in the array. So you partition A into the lower and upper parts, those which are smaller than the pivot, those which are bigger than the pivot. You rearrange the array so the pivot lies between the smaller and the bigger parts. And then you recursively sort the two partitions. And this was the actual Python code which we ran, and we saw that it actually behaved not as well as merge sort. Even for a list of size 7500, we saw it took an appreciably long time. So what is the worst case behavior of Quicksort? So the worst case behavior of Quicksort comes when the pivot is very far from the ideal value we want. So the ideal value we want is the median. The median would split the list into two equal parts and thereby divide the work into two equal halves. But if the pivot happens to be either the minimum or the maximum value in the overall array, then supposing it is the maximum, then every other value will go into the lower part and nothing will go into the higher part. So the recursive call would consist of sorting n-1 elements. So if one partition is empty, the other one has size n-1. So this would happen if the pivot is one of the extreme elements. And if this happens, and this is the worst case, then in order to sort n elements, we have to recursively sort n-1 elements, and we are still doing this order n work in order to rearrange the array, because we don't find this until we have sorted or gone through the whole array and done the partitioning. So this says Tn is Tn-1 plus n, and if we expand this, this comes out to be exactly the same recurrence that we saw for insertion sort and selection sort. So Tn would be 1 plus 2 up to n, and this summation is just n into n plus 1 by 2, which would be order n squared. The even more paradoxical thing about Quicksort is that this would happen if the array is sorted either in the correct order or in the wrong order. Supposing we are trying to sort in ascending order, and we already have an array in ascending order, then the first element will be the smallest element. So the split will give us an array of n-1 on one side and 0 on the other side, and this will keep happening. So the worst case of Quicksort is actually an already sorted array. Remember, we saw that for insertion sort, an already sorted array works well because the insert step stops very fast. So Quicksort is actually, in the worst case, doing even worse than insertion sort, and specifically on already sorted arrays. However, it turns out that this is a very limited kind of worst case, and one can actually try and quantify the behavior of Quicksort over every possible permutation. So if we take an input array with n distinct values, we can assume that any permutation of these n values is equally likely, and we can compute how much time Quicksort takes on each of these different n permutations, and assuming all are equally likely, if we average out over n permutations, we can compute an average behavior. Now this sounds simple, but mathematically it is sophisticated, and sorting is one of the rare examples where you can meaningfully enumerate all the possible inputs and the probabilities of those inputs. But if you do this calculation, it turns out that in a precise mathematical sense, Quicksort actually works in order n log n in the average. So the worst case, though it is order n squared, actually happens very rare. So the worst case actually arises because of a fixed choice of the pivot element. So we choose the first element as the pivot in our algorithm. And so in order to construct the worst case input, if we always put the smallest or largest element at the first position, we get a worst case input. This tells us that a sorted input, either ascending or descending, is worst case for our choice of pivot. Supposing instead we wanted to choose the midpoint, we take the middle element in the array as our pivot. Then again we can construct a worst case input by always putting the smallest value and working backwards so that at every stage the middle value is the smallest or largest value. So for any fixed choice of pivot, if we have a pivot which is picked in a fixed way in every iteration, we can always reconstruct a worst case input. However, if we change our strategy and say that each time we call Quicksort, we randomly choose a value within the range of elements and pick that as the pivot, then it turns out that we can beat this order n squared worst case and get an expected running time, again an average running time probabilistically, of order n log n. So as a result of this, because though it's worst case order n squared, but on average order n log n, Quicksort is actually very fast. What we saw is it addresses one of the issues with merge sort, because by sorting the rearranging in place, we don't create extra space. What we have not seen, and which you can see if you read up another book somewhere, is that we can even eliminate the recursive part. We can actually make Quicksort operate iteratively over the intervals on which we want to sort. So Quicksort, as a result of this, has turned out to be in practice one of the most efficient sorting algorithms. And when we have a utility like a spreadsheet where we have a button which says sort this column, then more often than not, the internal algorithm that is implemented is actually Quicksort. We saw that Python has a function l.sort which allows us to sort a list built in. So you might ask, for example, what sorting algorithm is Python using? Very often it will be Quicksort, although in some cases, some algorithms will decide on the values in the list and apply different sorting algorithms according to the type of values. But default usually is Quicksort. So before we proceed, let's try and validate our claim that Quicksort's worst case behavior is actually tied to the description of the worst case input as an already sorted list. So here we have, as before, our Python implementation of Quicksort, in which we have just repeated the code we wrote before. Now we are going to write another function which will do the following. It will shuffle the elements of a list by repeatedly picking two indices and just swapping them. So this will allow us to take, say, a range output which is sorted and create a suitably random shuffle of it. So here is the code for it. So it's very simple. You use a Python library called random, which allows you some functions to generate random numbers. And one of the things that this library has is this function rand range. So rand range generates an integer in the range 0 to length of L minus 1. So we pass it a list and we repeatedly pick two indices j and k in the range 0 to length of L minus 1, and we exchange Lj and Lk. And how many times we do this? Well, we just do it a large number of times. In this case, say if we have 10,000 elements in the list, we'll do this 5,000 times. We do it length of L by 2 times. So let's see how this works. So we load, as usual, the Python interpreter, and then we import Quicksort, and then we import randomize. So you can do this. You can write Python functions in multiple files and import them one after the other, and they will all get loaded. Now, as before, we will say L, for instance, could be the list. So let us also import sys and finish off that recursion limit business, because we know this is going to kill us. So set a large recursion limit, and now we set up a fairly large list. We had done last time, for instance, 7,500 down to 0. Okay. And what we saw was that if we try to quicksort this list, it takes a long time because it's 7,500 and it's a worst case input. Right? So what we are going to try and do now is, and the same thing will happen even after it's sorted, because even after it's sorted, it's still a worst case input, except now it's in ascending order. So both descending order and ascending order take a long time. So now supposing we randomize L. So if you look at L now, you can see that the numbers are no longer in order. Okay, so you see some 6,000 between the 7,000s and 2,000s and so on. So our claim is that this will go faster, and indeed you can see that if you run Quicksort on this, it returns almost immediately. Okay? And it's not because Quicksort has become any faster, it's because the order is in. Because again, if you run Quicksort on the sorted list, again it's going to be slow. Okay? So this just demonstrates in a very effective way that if we randomize the list and we run Quicksort, it comes out immediately. But if we don't randomize it and if we actually ask it to sort the sorted list, then it takes a long time. So you could actually check that, for instance, if we go back to this list and we make it, say, even something bigger like 10,000, maybe 15,000, and then we randomize it, and then we sort it, right? It comes out pretty fast. So this validates our claim that Quicksort on an average is fast. It's only when you give it these very bad inputs, which are the already sorted ones, that it behaves in a poor manner. Now there is one more criterion that one has to be aware of when one is sorting data. So very often sorting happens in stages on multiple attributes. For example, you might have a list of students who are listed in alphabetical order in the roll list. After a quiz or a test, they all get marks. Now you want to list them in order of marks, but where there are ties, where two or more students have the same marks, you want to continue to have them listed in alphabetical order. So in other words, you have an original order in alphabetical order. And then you take another attribute, namely marks, and sorting by marks should not disturb the sorting that already exists in alphabetical order. So what this amounts to saying is that if we have two items in the original list which are equal, then they must retain the same order as they had after the sorting. So I should not take two elements that are equal and swap them while sorting. And this would be crucial when you're using something like a spreadsheet, because if you sort by one column, you don't want to disturb the sorting that you did by another column. Unfortunately, Quicksort, the way we have described it, is not stable, because whenever we extend a partition in this partitioning stage or move the pivot to the center, what we end up doing is disturbing the order of elements which were already there in the unsorted list. So we argued earlier that disturbing this order does not matter because anyway we are going to sort it. But it does matter if the sorting has to be stable. If there was a reason why these elements were in a particular order, not for the current attribute but for a different attribute, and we move them around, then we are destroying the original sorted order. On the other hand, merge sort, we can see, is actually stable if we are careful to make sure that we always pick from one side consistently if the values are equal. So when we are merging left and right, when we have the equal to case, we have to either put the element from left into the final list or right. So if we consistently choose the left, then it will always keep elements on the left to the left of the ones on the right, and therefore it will remain a stable sort. Similarly, insertion sort will also be stable if we make sure that we move things backwards only if they are strictly smaller. When we go backwards and we find something which is equal to the current value, we stop the insertion. So insertion sort, merge sort are stable sorts. Quicksort, as we have described it, is not stable, though it is possible to do a more careful implementation and make it stable.